Okay, so first thing I have to warn you about is, for now, this is what most of you are going to want to follow along with. This right here is super important for this topic number 1, standard form. We're going to have to recognize that. So you definitely need to commit this one. As we practice today, you'll see that it's not so bad, and you'll get the hang of using it as we practice more. But super important number 1. Super important number 2 is this thing we call the integrating factor. Okay. Everything else I'm about to show you is just where this stuff comes from. Okay. So for those of you who, that's enough calculus for you at the moment, then take a break and you can follow me. But for those of you who actually want to see why this actually makes sense as a technique, I'm about to show you. So this integrating factor, this is a very clever way of solving a differential equation that yesterday we didn't have a method to do. And that's when they're of this form here, where we can't just separate them by dividing and multiplying across the equal sign. We have to do something more to it. So what I'm going to do is I'm going to call this y prime instead of dy dx. And again, if you're brave, you want to put this in your notes so you can copy along and understand where it comes from. But for our purposes, the technique of using 1 and 2 is going to be the lesson today. So what I'm going to do is, and this is a clever technique, okay? I don't know who thought of this first, but it is a very clever technique for solving this kind of equation. We call this a linear, oops, there's an I in linear. We call this a linear differential equation because the y component here is by itself. It doesn't mean the x's couldn't be like x squared, sine x, or x cubed. But what we're saying is the y in this problem is just a single y. It's not a sine y, not a y squared, not a y cubed. So it fits that pattern as long as somehow I can fit it into this form. Now, as I said, it's a clever technique, and what I'm going to do is show you sort of why it works. If I multiply this integrating factor onto everybody here, what I'm going to end up with then is y prime e to the integral of px dx. Then I'm going to multiply it onto here too, plus e times the integral of px dx, and, whoops, there's not a d there, that's a y, equals qx times e. So that may be, I don't know if that qualifies, but that may be the scariest looking thing we've seen so far in calculus. Anyway, let's see, vote, is that the scariest thing you've seen so far? It's pretty scary, I admit that. But again, this is not our lesson today. This is why the technique works. So again, if you're not feeling like you can follow this, just remember number 1 and 2 here are what really count today. So now you may not recognize it, but the reason that's a clever thing to do is if I look over here at this part of my differential equation right now, you may not recognize it, but that's product rule. So this is the derivative of the first function times the second, plus the derivative of the second times the first, right? The derivative of this piece here, there's an integral on it. So when you take the derivative of an integral, you just end up with what you started with, p of x, right? So that's where my derivative happens here. And the exponential function has that awesome derivative that is just the same exponential function. So it's hard to recognize, but this is actually the same thing as if we condensed it to say it's the derivative of y times e to the p of x d of x. Now why would we want to do that? Why is that clever? Remember, our goal is to integrate. So if we have a derivative, it's a very, very easy integral. Okay? So this is going to be equal to qx e to the p of x dx. And if I do this as the differential equations that we've been studying, that means I'm going to have to integrate both sides. And by integrating the derivative, it's not that it's not a scary looking thing, but that's an easy integral to do because the derivative is right there. It's going to be equal to this thing. And I can rearrange this now for y. And let me explain once I do that why this has any sort of advantage to what we started with. Oops, back that up a second. To q of x e to the px. So where we started, we had an implicit equation, an equation that had x's and y's on both sides. And if you follow the work that I've done here, you'll notice now I have an equation that has an integral in it, just like a differential equation would.